Good morning. I'd like to start also with many thanks to the organizing committees and the scientific committees for all the hard work for putting together this conference. And a special thanks to Michele, who has been working so hard on every detail of this conference. I'm really very much appreciate the opportunity to share some of the recent research in my group. I'm going to talk about three things, and I'll try to tie them together under the general umbrella of generalized BNP. First, some acknowledgement. The work is done with my former student, Naoki Awaya, who's currently assistant professor at Waseda University in Japan, and my current postdoc, Yuliang Xu. And all of the research was funded by the NSF and NIH. So nowadays, I believe that probably every one of us have been bombarded with news about various kind of applications of generative AI and generative models. We've heard stories about people using generative models to design new proteins and drug design and so on and so forth, right? And but as a Bayesian modeler, generative modeling seems to be something we have been doing for a long time. In the current context, in the machine learning community, the focus is generally in learning or estimating or sampling from a sampling distribution that can generate very complex data, right? And in the current context, usually in the AI community, when they talk about generative models, they were thinking about some algorithm that allows you to either come up with a point estimate of a very complex sampling distribution, or some sampling distribution that can allow you to draw samples from a fixed distribution, right? So some of the very popular models include these ones. And then usually when they actually design these models and they adopt very flexible, sometimes unstructured characterization of the underlying distribution, right? So for example, the very popular method of the day, like diffusion models and so on and so forth, is based on modeling the underlying gradient field of the distribution, which is generally pretty unstructured. And because of that, because of the complexity of the distribution, also the the unstructured nature of the parameterization, you need to use very flexible classes of functional approximators to actually approximate them. And deep neural networks becomes kind of the choice, the everyday choice for most machine learners. Now, on the other hand, as I mentioned, as a Bayesian modeler, it seems to be something that I feel very familiar with. The reason is that for the past decade, or in most of my career, I've been thinking about modeling sampling distributions and putting priors on them, thinking about the uncertainty that are induced by the prior and the sampling distribution, right? So there are some commonalities between the current generative AI focus and also the traditional Bayesian nonparametric focus, which is to try to capture the complexity of a sampling distribution, right? But there's also some differences, right? So traditional classical BNP models usually use pretty structured parameterization and function classes to represent the underlying sampling distribution. For example, discrete mixtures, Gaussian processes, and in the case of tree models, usually, for example, a single tree, BOT is kind of starting to deviate from that paradigm. Right. So there are benefits of using structured parameterization because it allows you to have more interpretable results and so on and so forth. But in recent years, there's also a general trend of moving toward more flexible parameterization of the underlying sampling distribution. And various strategies that have come up in this community involve like multi-layer modeling, more complex hierarchical modeling, as well as, for example, additive ensembles, which I will touch upon later today, and also which is what BOT is about, right? So I'm not going to talk about specifically how in this talk we use additive ensembles to build generative models. If you're interested, I had a previous webinar which is recorded on YouTube. In particular, the second half of it, we showed a connection between additive ensembles in the case of generative modeling to normalizing flows. And if you're interested, you can take a look at that. And so my view on this is that there's very close connection between BNP and generative AI and generative models. The only difference seems to be the focus. So in traditional BNP, we start off with very structured sampling distribution, and our focus is on how we design reasonable priors on that so that we can get good properties in the posterior inference and so on and so forth. I would encourage our community to shift focus a little bit more toward building very flexible and reasonable sampling model. It's still part of the Bayes theorem, but in order to capture very complex distributional features in real life, in very modern complex distributions, we can't live with just very simple structured function parameterizations. If you start off with that, then a lot has already been lost, and no matter how you do on the prior part, it won't resolve the deficiency in the likelihood. Now, at the same time, there's also a general trend in our field, which is great in moving toward robust inference or generalized Bayes inference, because there's a recognition that if one starts to use very flexible parameterization of the sampling model, then sometimes sticking with using kosher likelihood-based Bayesian inference becomes very difficult. There's two ways this difficulty can arise. One is that the model can be so flexible that you may not even have an analytic tractable likelihood, and you have to do something else. And the other way may be that the likelihood is available, but it's so complex that there's no easy way to carry out the computation or doing the inference. And then maybe you have to give up some core features of Bayesian inference, for example, uncertainty quantification, by doing things like optimization, variational Bayes, and so on and so forth. You have to make some compromise on that. But another type of compromise, which I will make in this talk, is to deviate a little bit away from the kosher likelihood paradigm to go into the generalized Bayes paradigm using loss functions as a substitute for likelihood. And in fact, as a result, it will allow you to do practical Bayesian computation and inference because of the fact that the original likelihood is either not available or too sophisticated to carry out practical computation. So I'm going to start off with some data example to motivate the talk. Right? So I've been working on microbiome data sets for a while. So microbiome data set, for those of you who don't know what microbiome data set is, that you can think about there are many different bacteria living in your gut. And people like to measure the amount of different bacteria that live in your gut. So they take a fecal sample and then they do sequencing experiment. And that allows you to figure out the relative proportion of different bacteria species that are living in your body, right? So in these studies, it's kind of different. This is an active research area of how you can apply generative models, generative AI to this biomedical setting where the data is not image or video and so on and so forth. And in these settings, the objectives are quite different because if you're generating text or videos, sometimes you just need to make sure that the text and video you generate look realistic and they're diverse. They're not always giving you the same video and then they look nice. Whereas in the scientific setting, you want more than that, because if you're using your model to characterize the underlying distribution of microbiome compositions of a population, you might as well get that distribution correctly, because otherwise your modeling and the inference downstream is going to be incorrect, right? So this is an example. This is the data from the Human Microbiome Project. And each column here is a colored bar of the proportion of different microbial species. Now, we did some groupings based on their genetic relationships, so that because the data is 122 dimensional, so it's hard to see. So we did some grouping based on their evolutionary relationships so that you can see a single color for some species that are closely related. And the top bar is the real data, and the bottom bar is something. I'm going to compare several generative models. And the purpose of this is not to tell you which generative model is the best for microbiome data, but to illustrate a point that in practice, one needs, it's an important statistical problem is to assess and tell which generative model is good. All right, so I'm not going to actually focus on any particular generative model, but just to demonstrate the need for new statistical methods and paradigms to actually assess the quality of generative models. So the first model we look at is the Dirichlet model. So it's using Dirichlet distribution as a sampling model, not a prior, a sampling model, repeated drawing exchangeable samples from the Dirichlet distribution. And you see that, and this is based on a MLE point estimate of the above distribution. And you see that it doesn't capture the distribution very well. And then the second distribution is in the frequentist literature called Dirichlet tree, but in our world, it's called Polya tree, except that in the non-Bayesian literature, they're using it as a sampling model, whereas we're using it as a prior. So this is basically repeatedly draw samples from a Polya tree where the beta distribution is no longer the prior, but the sampling mechanism for each left and right split. Well, it does a little better because why? Because it allows you a little richer covariance structure, right? Because even though the betas are independent, the tree structure induced some correlation structure among the generated proportion. And the tree here used is the so-called phylogenetic tree of the microbial taxa. So they capture some biological relationship among them. And therefore, as you do a little better with the covariance structure on the sampling model, you do a little better in the data characterizing the distribution. However, using independent betas across the tree node is still very restrictive. So a more recent work from my group a few years ago, actually the paper is still under review, it's been very long, is that one can further allow some kind of a richer covariance structure across the tree nodes when you do the sampling distribution, model the sampling distribution along the tree. This work is very much inspired by a seminal paper by Alejandro and Tim Hansen in 2010, where they introduced this logistic Gaussian process along the tree structure. In their work, they induced a dependency structure over covariance. In this work, we introduced covariance structure within the tree, not along across covariance, but across tree nodes. And it does better. If you can see just the bars of the data, it does look better. It starts to capture the data more and more. Now let's move into the more unstructured generative AI type of algorithms. So this one is called flow matching. It's kind of one of the state of the art for fitting normalizing flows. And the version of the flow matching I'm using, I'm not going to talk too much about normalizing flows. If you're interested, you can look at some references, and also it's related to the previous webinar that I gave. And you see that it does better, right? And the way it parameterizes things is very unstructured, basically using some kind of optimal transport type of strategy to figure out a field that transforms a noise distribution into a very complex distribution. It does better. The last one that I show is generative adversarial networks, which is GAN. And in this particular data set case, it seems to be doing a little better too. But I have to say that once you're in the very flexible class of sampling models, it's a little bit hard to assess which one's better than others. Okay, it's not so clear, right? Another way to look at them is to look at how the generative model preserves the pairwise differences of your sample, right? So you can do a dimensionality reduction plot. This is a PCOA plot that just looks at the yellow points are the generated samples from your generative models, and the blue points are the real sample. And you can compare like how the pairwise relationships of the samples are preserved. And Dirichlet tree or Polya tree clearly misses a lot. And then the logistic tree normal gets pretty good among parametric models. And once you're in the fully non-parametric deep neural, these are all deep neural network-based methods. In the flow matching and also the GAN, they found just this plot, it's already very hard to tell which one's doing better because they all seem to be preserving pairwise distances pretty well. Yeah, well, up to this point, you may get the impression that maybe I'm being very pessimistic about parametric models and we should ditch them. That's not the point I'm trying to make, because parametric and structured models have their benefits. It's easier to interpret, it's easier to generalize, so it has its place. But the focus of my talk here is that given all these kind of very flexible and effective sampling distributions, how do you assess them? How do you compare them? How do you tell that which one is a better generative model? Now, if you open some conference proceedings, this is from a seminal paper. I think if you want to read one paper about generative models recently that tells you the state of the art, this is the paper that I would recommend reading. right? But the point here is that in the typical paper in the AI literature, you will see a table like this. A new method is introduced, and it does a comparison with all like 200 other methods that was introduced. And the comparison is based on some numerical scores. So you may use out of sample negative log likelihood. You may use something called FID, which is just basically empirical Wasserstein distance between the generated samples and the real samples. And you might see something called inception scores, which is basically not a distance metric between distribution, but a assessment numerical score just summarize the generated samples. For example, looking at the quality of the samples as well as the diversity of the samples, with not regard to the actual real distribution that's being the data, training data was coming from. So scalar summaries are good for some purposes. For example, they're good for ranking, if you just want a simple ranking. And they're also good in a more upstream stage of fitting generative models. They are good for detecting overfitting and so on and so forth. But they're inadequate to tell you exactly how they are doing better or worse and the nature of the underlying deficiency so that you can improve your model. Just by looking at these numbers, maybe you can see that the last method that was introduced in this paper is doing better by every score, but how much is it better and can you further improve it is hard to tell from the numerical score. And to me, that's a statistical problem, right? You have, and it's a very old statistical problem, you have exchangeable points, ID points from P, which is the real generative distribution, and then you have a set of data points from Q, which is coming from your generative model, right? Now, a century ago, or maybe for very much of the last century, is that one can formulate this as a hypothesis testing problem of whether P is equal to Q or not. But in this day and age, this is not sufficient because every model is wrong and every generative model is definitely wrong. And there's no question that H0 is never true. The point is that one needs to have an effective summary of the underlying difference, knowing that there must be a difference, and ideally also have uncertainty quantification. So you can actually give confidence about your statement about the misfit of the generative model. So these are going to be the goal here. But before I get into the more technical detail, there are some caveats. I want to say that once I'm actually formulating this problem as a statistical problem, I already lost something because I'm already starting to make assumptions. And that involve assumptions that may or may not be satisfied by the generative model. For example, if the ID assumption is violated, right? Or let me give you an example. If somehow your generative model is as bad as just outputting exactly what the training data is, okay? Think about that. You had a data set, you did training and testing split, you reserve the testing data as the P in your assessment stage and use the training set to fit your Q. And then your generative model is so bad that it just gives you whatever training data overfit badly. But they're from the same distribution because it's your training testing split. So that kind of issues cannot be detected at this stage. It has to be detected in the training stage. So one has to be a responsible machine learner to do that. Okay, so those are the caveats. But assume that you're responsible. You've done your careful checks to avoid these kind of overfitting, double dipping issues. You arrived at this stage. You want to assess and compare generative models. And with regard to their relationship of the original real data, this is the formulation here, right? And the point is that I want to make the point that because the underlying sampling distribution is so complicated, one should not just use a scalar or even a very low dimensional summary to characterize their difference. Because if the underlying sampling distribution is infinite dimensional complex object, then the summary of their difference should also be functional. And secondly, beyond just a point estimate of their functional difference, there also needs to be uncertainty quantification. And this is where the BNP, the Bayesian part will come in, but you have to be patient and bear with me because this is going to be the last bit of the punchline near the very end of the talk, right? So, so here's the outline of the rest of the talk. So I'm going to start off just with some kind of a functional summary of two sample differences and think about what might be good functional summaries for two sample differences, and then think about how do we learn them when we're provided with two sets of data. Which loss function should we choose? I already gave you a hint that I'm not going to use the likelihood as the loss function because in this case, they are not available in closed form, right? Which loss function to use, which classes of functions to under that loss to approximate the density, the quantity that characterize the difference. As the title of my talk suggests, I'm going to use additive trees. And finally, the last bit of the talk will be about how you do Bayesian inference in this context. All right, so it turns out that there's a candidate that has been studied in learning theory a lot, and I'll refer to Long's paper about 15 years ago, which inspired a lot of the thinking downstream. Yeah, and Long is one of my local heroes here. So so this idea of summarizing two sample difference. So one notion of distance that has been studied a lot in learning theory is something called F divergence. And it generalizes the notion of KL divergence. So if you have two densities here, P and Q are two measures, you can generalize that. Then the KL, we're all very familiar with that, right? And you can write it as the expectation under Q of some function involving the density ratio between P and Q, okay? And then a generalization to KL is the so-called F divergence. It turns out that you can form notions, other kind of F divergence by simply replacing this function F with other functions of the density ratio. And as long as the function satisfies convexity as well as some basic properties, it will be fine. And many common distance metrics can be written as an F divergence. So for example, KL divergence is this. And then for total variational difference, distance is that. And then we're going to focus on the squared Hellinger distance in this talk. And you'll see the reason why. There's several reasons why Hellinger distance is particularly nice. Okay. And finally, chi-square divergence. Right. So, what's so nice about the density ratio? So my first argument is that if you want to summarize the difference between two samples, you may want to first get a hold on the ratio of the two densities as a summary. Now, I'm going to wait until later to tell you what might be a reasonable strategy to get a hold of on the density ratios. But for now, let's just imagine that if I know somehow the density ratio, then what can I learn about the two samples? All right. So first of all, by the definition of F divergence, there's a very nice property is that the F divergence, if you do a change of variable that goes from the original data point, no matter how high dimensional your data is, but if you just apply the change of variable to go to the density ratio, which is a scalar function, it's a univariate random variable, then the F divergence between the univariate random variable, the distribution of the univariate random variable under one sample and the other is the same as the original high dimensional data that you have. In other words, the density ratio preserves two sample differences if you measure two sample differences using any of the F divergence of your choice. All right, so that indicates, and also this result follows very immediately from a classical statistical result, which is that the likelihood ratio is a sufficient statistic for the two distribution family of P and Q, and that's it. And it turns out that we also know that the likelihood ratio is a minimal sufficient statistic in the sense that there is no other univariate transform that's simpler than the density ratio that preserves the F divergence in this case. So let me give you an example. This is the microbiome example that I showed you. And these are the 6 generative models going from Dirichlet tree LTN, the full matching, 2 variants of full matching, and then the last one's GAN. And the yellow and the blue are the histograms of the density ratios that are estimated on the two sets. And you plot the histogram. It gives you in my view, more concrete sense of how close the two distributions are to each other. The original data is 122 dimensions. And this is a one-dimensional summary. And now it seems that it's much easier to rank or to tell how much better GAN is. And you can do more with it. So this is just the dimensionality reduction plot that we saw earlier without the density ratios, where you can see some general misfit, but it's hard to rank these very complex models in how they exactly fit the real sampling distribution. But if you color the points and label them by the estimated density ratio, right? So you see that the density ratio is P over Q. So the more red it is, meaning that the density ratio is higher in favor of the real distribution, and then more blue it is higher in favor of the generative model. The ideal case is that if everything is just in the middle range is white, meaning that the density ratio is more or less 1 everywhere, right? So this is the GAN. And the lighter the color is, the better the indication that the generative model is fitting the real data better. And you see that these more flexible models are doing better. And the parametric models, the LTN, does pretty better than the other ones, but still have very dark blue and red. All right. But up to this point, we have no uncertainty quantification. And one may wonder that, well, maybe you're just lucky with this GAN model for this data set, and they're really not that great, but you can't tell. So if you can also get uncertainty quantification, then you can get the middle 95% Bayesian generalized Bayes, as you can see, quantiles of this density ratios, as you will see. This is the lower bound, 2.5, and this is the upper bound. The lower bound is more blue, and the upper bound is more red. But in any case, for the GAN in this case, the lower bound is pretty much all red and all blue, and then even though it's very you cannot see, I can see it here, but you cannot see it. So this plot is very, very light blue. And then this plot is, the upper bound is very, very light red, indicating that indeed the credible band, the kind of really very much zero is in the middle of that 95% credible band. And that I can be pretty confidently saying that from the Bayesian perspective, there's no really obvious reason to think that this GAN in this particular data set is doing very poorly. So if you don't have uncertainty quantification, then it's everybody's guess, right? So if there's questions, I welcome. You feel free to stop me. So now I'm going to get into the technical bit. I'll move a little faster. So first of all, we have to pin down. Hopefully by this point, I have convinced you that learning the density ratio is useful for the purpose of comparing two samples. And this is not a new strategy. There's a literature on learning density ratio in the machine learning community, in the CS community, based on various different approaches. And there are two approaches that are particularly relevant to my talk today. One is this approach called using the variational form of F divergence. And the other is the so-called density ratio trick, which is fitting a binary classifier and flip the classification rule, which is very popular, arguably the most commonly used approach to estimate the density ratio, if you would, in the machine learning community. I'll show you that our approach can be motivated from both perspectives, but it's not going to be exactly the same as inverting binary classification. And in fact, I will try to convince you that inverting binary classification is sometimes not a good way of learning density ratio, because if your goal is to do classification correctly, it can contaminate and make your estimate of the underlying density ratio not very reliable, especially in unbalanced sample sizes. And people know that. I think a lot of people know that. So of course, in the literature, there's also different classes of function classes that have been used to approximate the density ratio. I noticed that some of my own work using models that generalize polynomial trees based on an adaptively learned prediction can be thought of as using a piecewise constant approximator to the density ratio, even though we know that a single piecewise constant function is very limited to approximate flexible functions. So later in this talk, I will generalize to additive ensembles of trees that kind of in a BART flavor that allows you to approximate the density ratio more effectively. And all the examples that you've seen are estimates and posterior credible bands coming from a BART model, BART-like model. All right. So I mentioned that other than the BNP approach, everything else ignores uncertainty, gives you a point estimate, and that's it. Call it a day. And you can't really do bootstrap. If you have high-dimensional data, bootstrap won't work, right? So so you have to be careful, right? So so let me start off with talking about the F divergence, because this is going to be the starting point. I'm going to mainly motivate the approach from the variational form of F divergence. F divergence is, in principle, a very nice summary of the distance between two distributions. The problem, though, is that if I give you a data set, directly, there's no way to come up with a estimate for it, right? So one way to do it is to reformulate it as an optimization problem. So this is called a variational form of F divergence, which is studied in a Long's paper, which I cited earlier. It's a great paper. I recommend everybody to read it. So it turns out that if you want to learn the F divergence between the two measures, you can formulate it as an optimization problem that involves two expectations. One is the expectation under one sample. The other is the expectation under other samples. And then based on your choice of this F function, then there's a corresponding notion called the convex conjugate for F, which basically is given once F is given. And the rest, what you do next is to optimize to find the maximum of the objective over a suitable function class. And the function class is your class of functional approximators. It could be deep neural networks, it could be tree models, and so on and so forth. If the model is rich enough, if the function class is rich enough, which can capture the exact truth of the underlying density ratio, then this becomes an equality. So it's variational in the sense that if your function class isn't there, then it's approximation. It cannot achieve the actual F divergence. But if your function class is rich enough, you can, right? So now, of course, there are many different choices of, so why do we do this? Because this is going to give us a gateway of formulating an actual loss function and optimization problem so that we can actually estimate the F divergence. And because the optimizer for the right-hand side objective function is going to be a one-to-one transform of the density ratio. It gives you an estimate for the density ratio, right? But you have many different choices of F divergence. Not all of them are equally good. Because if you look at the function definitions of, let me not go all the way back, too many pages, but in modern applications, the overlap of the support of the two samples are usually not perfect. So you may often have regions in the sample space where one sample has very little mass and the other have quite a bit. And then if you have that in the denominator, the density in those sparse regions, you can have a numerically unstable F divergence. So not every F divergence is equally good. And in particular, this is just, in this example, we're actually just trying to solve the optimization problem, the variational form of an F divergence using deep neural network. And at the x-axis is the number of epochs. And you see that if you choose chi-square divergence, it diverges, right? Because the denominator is actually unstable. And then KL is supposedly unstable, but it actually goes to infinity very slowly, and it often gives you reasonable point estimates as well. Our choice is going to be the Hellinger loss. It's bounded. It's a bias variance trade-off. It never goes to infinity, even when the support is not overlapping, but you do lose some kind of efficiency in that sense. It's a trade-off. All right, that's not the only reason we choose Hellinger. I'll tell you more. The Hellinger really induces some magic in this context. So this is the Hellinger distance, square Hellinger distance. And then the corresponding convex conjugate is this function. And then basically the variational form is to minimize over functions that are less than a half on this objective. And the optimizer is going to be this G star, which is a function of the square root of the population level density ratio. And this is an M estimation problem. So one can study general theoretical properties like consistency and convergence rates using tools for M estimation. And in Long's paper, they studied it for the KL F divergence, and where and the techniques can be modified to study the Hellinger as well. I don't want to gloss over the theory because it's not that I don't think the theory is important. The fact that I'm not giving a lot of detail is that I haven't reached a point where I'm very proud of the theoretical results that we're working on. So stay tuned, maybe, hopefully next time. So because I think that for the class of functions, the additive trees and so on and so forth, there has been so much going on in our community in the last few years. Ishmael and Veronica, a lot of people have done great work theoretically for for additive trees, and I think we can push it further. So, but at this point, I don't have very satisfying theoretical results to report. All we have is some kind of a minor tweaks of Long's results to adapt it to the Hellinger distance. So I'm not going to present those here. So finally, later I will touch upon it, is that other than the robustness property of Hellinger distance that encouraged us to use it, another magic that happens later is that it really makes generalized Bayesian inference simple. Remember, generalized Bayesian inference is using the loss as the pseudo likelihood and put priors on it. And therefore, the form of the loss function actually really is relevant in terms of how you do Bayesian inference, generalized Bayesian inference down the road. And it turns out that Hellinger distance is very, very simple for doing downstream Bayesian analysis. So I'll show you why. So to do that, let's do an equivalence transform of the Hellinger loss. So previously we have this function g, but let's do a change of variable, do this, rename this function w as a function of g. And then you can show that maximizing the variational form, the right-hand side of the Hellinger loss, is equivalent to minimizing this loss function or the population loss function, and it's symmetric, involving the w function. So it's simpler, and you can show that the population minimizer for this loss is going to be simply the square root of the density ratio of the two families. Okay, so there's actually intuition of that. You can show that what does this function do? And we call it w for a reason. You can think of it as a weighting function. It's a weight function. What does it do? If you have two data sets, right, and they have different distributions, if you weight one sample, the sample from P using W inverse, and then you weight the generated sample using W, okay, then after the reweighting, the two distributions are equal. In other words, if you give me any measurable set B, the sum of the weights of the two samples after the reweighting, originally they're not weighted, they're not equal, they're different measures, but after weighting, using this weight, they are equal. In this case, the dots, there are more dots than triangles in one sample than the other, so the original measure, the dot measure will be higher, but after the reweighting, they're going to be equal. So we call them balancing loss, right? So it has an interpretation. And why do we write it down using this equivalent form? That goes to, and there's a simple empirical version of this loss, which is just the sample average between the two classes of the weights. Why do we do that? Now here comes the binary classification problem. So in binary classification, a common loss function that people use is so-called exponential loss. It takes this form, right? And then Z is, you're now in a supervised learning problem where the label is -1 and 1, which is the Z, and then you have some predictors, X, right? Here, previously in the two sample case, I use X and Y both to be predictors in this case, and the label, group label being the label. And in binary classification, the loss function, the population level loss people use, is the joint expectation of the label and the X, and it looks like that. Now, again, let's do a change of variable, rename W to be the exponent of -f, then it looks terribly like the balancing loss that we just saw. The only difference is that the two pieces of the loss contribution from the two samples is reweighted by the population abundance of the two groups. Now, why is that important? Because the objective in classification is actually get the label correct. So of course I'm gonna penalize more, give more weight to the more abundant group, right? So, and if you compare the two loss functions, that's the only difference. And the optimizer for the exponential loss is gonna be the posterior odds of the two samples, not the density ratio. It's the density ratio times the prior odds, okay? And this is what people use as so-called density ratio trick in machine learning. To get the density ratio, they do the binary classification, and they invert it by the marginal proportion of the two groups, and they get the density ratio for various purposes. I think Veronica had two very nice papers, the Metropolis Hastings by classification, where the density ratio trick was plugged in to get the ratio in the Metropolis Hastings, and ABC by classification, also using the classification trick. So this is a very common technique. The problem, though, is that if the goal is using this to get the density ratio, why not just using the balancing weight? Then it won't be contaminated by the marginal proportions, right? So now here comes the almost last bit. I'm not going to run over all my slides, but try to stay in time. So then we have our choice of the loss function. Let's talk about the choice of the function class that we use to approximate this way. So we're going to be using the additive model, additive ensemble. So additive model, you model this F, the log weight, using the sum of a bunch of base learners, okay? And then in particular, we're going to do additive tree models. So each base learner is a piecewise constant function defined on the partition given by a tree, and on each partition block, you have a constant function, okay? And then if you use the balancing weight, which is equivalent to solving the variational form problem for Hellinger distance, then you just basically do the minimization problem over the parameters beta and the tree and over that loss function, okay? Now, at this point then you can formulate it. It's not surprising that you can solve this problem using some generic algorithms for fitting tree ensembles at this point, because it's so close to the exponential loss, and people have been fitting gradient boosting algorithms on exponential loss, and the only difference is that little constant of 1 over n and 1 over m. You can easily compute the functional gradient of this loss with respect to f, and then those are your pseudo residuals in your gradient boosting algorithms. You just throw it into your gradient boosting algorithm from Friedman 2001, and for fitting each step in the base learner. So the algorithm is you start off from uniform, you compute the loss, you compute these, given the current estimate of the weights, you replace your data points, x with these as your data point, and then these as your y points, and fit a cart tree model. And then you iterate, and of course you multiply that by a learning rate so that you impose regularization, you just aggregate that. It's a standard gradient boosting algorithm, okay? And you can do it, and now I made it red here. The only difference from a standard gradient boosting for classification is that the pseudo residuals are gonna have this 1 over n and 1 over m, which wasn't there for classification problem. And then secondly, it's very intuitive. So looking at what are your new observations? Well, the x observations, the more x observation you have, it will encourage you to increase the density ratio because increase p, so it's positive. The more y observations you have, it should be negative because it encourages you to reduce it. But the impact and contribution of each observation is downweighted by the way they've already achieved, right? So now, of course, gradient boosting was introduced in cases where you can't do functional gradient descent for your function class. But it turns out that I'm not going to have time to talk about it. It turns out that for this particular problem, we show that there actually exists a direct functional gradient descent algorithm. So you actually don't need to do gradient boosting if you don't want to. And you can actually do a vanilla boosting algorithm doing a forward stage-wise fitting of the tree. But I'm going to skip that because I don't have time. I'm going to spend the last 5 minutes talking about Bayesian inference. So now we finally arrived at a loss, which was serve as our pseudo likelihood, a function class, which is additive trees. The last bit is how do we do generalized Bayesian inference with it, right? So the model is just a additive tree model. So it seems that using a BART-like prior is natural. Let's just put independent Bayesian cot priors on each of the trees. But then what needs to be adjusted is what is the prior you put on the coefficients of the partition, right? So under the generalized Bayes framework, and Stephen can't be here today, but this is one area that he and Chris also and others have made major contributions to our community. And this really serves as the foundation of much of what I do here, is that you can use the exponentiated loss as your pseudo likelihood and impose the BART prior here and try to draw posterior inference. Now, then what's prior to use? What's needed? The key to success in a BART algorithm is the conjugacy of the full conditional of the betas. So in a BART regression problem, you have a Gaussian sampling model. That's why you need a Gaussian prior on beta to get conjugacy. Here, it's a little tricky. We have a funky shape pseudo likelihood. But it turns out that you can rewrite, if you look at the full condition of the likelihood, what does it look like? It looks like a 2-parameter exponential family. That's completely coming out of the Hellinger loss. And once you have a 2-parameter exponential family, you have a conjugate prior, which is the inverse Gaussian prior. So that if you impose the conditional prior as an inverse Gaussian prior on the exponentiated, on the beta parameters, you have full conjugacy. So the bar algorithm carries through just like usual, as in the Gaussian regression problem. Now, the one bit of nuance is that this prior, the way that we specify the prior on the beta is not symmetric. So the full conjugate update is not symmetric in XY. That doesn't seem right. Our prior on the density ratio should be centered around 0 after taking the log, because why would you a priori think the distribution should have one tail longer than the other? Well, the symmetry in the Hellinger balancing loss comes into rescue again, because it's symmetric in W and 1 over W. Let's just interlace them. Like when K is odd, you put inverse Gaussian on e to the beta. When K is even, you put inverse Gaussian on e to the negative beta. And that's it. It balanced it out. So approximately, marginally, it's a Gaussian prior on the density ratio at every point marginally. And then this is the tuning parameter, or you can put hyperpriors on it if you want. And then the rest of it, and you can put fully conjugate gamma priors on the temperature parameter. And that's it. You do the rest of it is just standard BART under the balancing loss and then the conjugate update, right? So I already showed you the real data example, so I'll just stop with a simulated data example. Yeah, David.
So I guess if you're using these generalized posteriors, this notion of them with these Gibbs posteriors, then there's quite a bit of subtleties, and so the temperature parameter is not something you can learn based on the data. So like it seems very odd to put a prior on it. Usually that has to be very, very carefully calibrated to give you kind of reasonable uncertainty quantification. Even beyond like kind of multi-parameter problems. There can be issues with using only a single parameter, temperature parameter. So I don't know how did you magically like put a prior on the temperature parameter and then learn an appropriate value? Like, do you have any results?
Yeah. So this is a good. So this is a great point. I haven't thought about it carefully enough. We thought that the analogy between this and the variance parameter in the BART algorithm is pretty natural. So we put a prior on it, and the posterior draws. I'm not showing the marginal posterior for the temperature parameter. Looks reasonable, but I haven't thought about it carefully enough. And you raised a great point. I will follow up with you on that, right? So and this is very new. This is so new to the point that we don't have a paper yet. Hopefully, a manuscript will come up within the next month or two. So there's a lot of moving parts at this point. So just stop with a simulated example. So these are 3 scenarios with global shift, and then a local shift. The mixture of distributions mostly the same, except for this mode. There's a little shift. And then in local dispersion, everything's the same except for this mode. There's a little more spread out in the red points than the black points. And then I'm going to skip the details of the competitors. I'm going to skip. I'll just show you some plot because I don't have time. So these are the point estimates for different methods for estimating the density ratio. This one is inverting at a boost. So the density ratio trick, right? For the global difference, it's still okay, especially when the sample size is balanced. These are 2 methods that are very popular in machine learning where you use Gaussian kernels to approximate density ratios. The point I want to make is that even if the samples are Gaussian, the density ratios can be far from Gaussian. Even if I just move the points a little bit, modify the spread of a Gaussian kernel a little bit, the divergence between them can be highly non-Gaussian. So it's not very stable. And it can do very, very poorly, even for Gaussian data. And then the bottom line is the boosting, gradient boosting I'm showing here. And this is the Bayesian predictive, the posterior mean, and then the lower and the upper quantiles for the density ratios. And this is the second example. Now, when the density ratio structure is actually very local, using the density ratio trick is very, very bad because the loss is mostly dominated by the vast majority of points where there's no two-sample difference. And then the two-sample difference exists only in the local region, then your loss function is dominated by the 50-50 split on the rest of the space. It's a very bad idea. And then, but in boosting, you do well, and tree boosting, and also you can get credible interval. And finally, I'll just show you one example. We also try to create a difficult situation where the posterior uncertainty will be large. The way we do it is that we create the two-sample difference in some embedding space, in some latent factor space, and transform it back to a higher dimensional sample space. Why is that hard? Because it's very hard for trees on the axis aligned partitions, and that results in higher posterior uncertainty. And when you have higher uncertainty in the posterior, and the problem is harder, uncertainty quantification becomes even more critical. And because you can see that even though the truth is that, and the colors seem to be spread out a lot, the credible regions are so wide that on those outer regions, the white parts are really sitting inside the credible region. Only the middle really two-sample difference, where the two-sample difference exists, is actually standing outside of the credible region, right? So I'm gonna stop here. So here's a quick summary, and then I thank you for all your time, and I hope you enjoy the conference.
Yeah. From this wonderful call, are there questions and comments? This is very exciting work. Going to the microbiome example, what's the feasibility of drawing samples where you've conditioned on some aspect of the sample? So for example, in power analysis, you might be interested in, like, suppose the 200 qubits factor radius ratio is like something. What would the rest of the sample?
Yeah, so this is another line of work in my group. I'm not presenting it here. This is more about developing generative models. So in generative modeling, usually the interesting application of generative model is not to generate samples from the marginal population distribution. You build a population distribution using a generative model, and then you combine it with a, in the machine learning community, called forward likelihood model, predictive model, and then you invert it by Bayes rule to draw so-called contextualized samples. So you train your generative model for a large collection of videos, but then I give you a condition. I want to see a video of a cat. You generate a video of a cat, right? So the same strategy applies here. As long as you can get a generative model for your microbiome composition. So this is an ongoing area in my work. I think maybe Ganchao, in your poster, do you have examples on that? Okay, we didn't touch that. That's fine. But Ganchao, where is my postdoc? He has a poster on building generative models improving them using Gaussian process. But it's very much the same. As long as you have a predictive model, you can invert it using either Langevin dynamics, and also in our group, we're exploring ABC type of strategies to do that. But essentially doing some kind of a inverse sampling based on Bayes rule when the likelihood is not available. Yeah, sure.
Thanks, Lisa. One of the big motivations was to get interpretability in terms of the difference in the distribution. So like in something like the microbiome example, where you're in this high-dimensional space and you have like a bunch of samples, like it's kind of maybe hard to like just look at the individual points in this high-dimensional space, and like lower-dimensional projections can be misleading. So like, how do you pick out like what actually is different about the distribution? Like we have a biometrica that shows a lot of the gender models back off the tails of the distribution, for example. So if you knew the variance was underestimated or some other aspect, that might tell you a lot, but like examining the individual points is challenging.
Yeah, so that's a great point, because interpretability is a problem. So along this line, I didn't present any results here, but along this line, our approach is a bit different from what you said. So what we're doing is that once you have the density ratios, you can try to see how that density ratios function is affected by different coordinates in the text set space. So for example, you may do something like a canonical correlation analysis and try to see which linear combinations of text abundance gives you the highest correlation with the density ratio gradient or something like that. So those are things we're exploring. I don't have very nice result I'm proud of, so I didn't include them here. We do have some results. Yeah. So. Yeah. Hello.
Just wondering for highly dimensional data.
Yeah.
Density ratio would be highly sensitive. So how do you do that?
Yeah. So basically, density ratio in high dimensional data, you can only learn it up to some level, right? So the regularization is important. There's two layers of regularization here. One is embedded in the loss, that we adopted a loss function that's not very sensitive to non-overlapping support, which is a critical issue in high dimensional data. The other type of loss regularization we impose is the additive tree model. Because the tree model, if you think about it, is the strongest regularizer in the tail. Because it's a piecewise constant. For the vast majority of the space of the sample space in the high dimensional problem, it's in the tail. And then the worst you can do is a very small constant as a tree. So I think in those two, by combining these two, we come up with estimators, hopefully, of course, I don't know the truth in every high dimensional problem, but hopefully we achieve a sweet spot in bias variance trade-off. Yeah. So we induce some bias in the tail to protect us from the instability of high dimensional problems. It's a very good point. Thank you all.